Okay, class, this is our video about the tables of linear, exponential, and quadratic functions. So open up your notebooks and we're going to fill in the bottom part of each tab that we created yesterday. So, in review, linear graphs look like lines. They can be written like y equals mx plus b, y equals some random number, or x equals some random number. And sometimes they can look goofy like this one here. So now we're going to look at a table of a linear function. And the key thing with the table, before we write any examples down, is that the x's and y's change at the same rate. This is important to pay attention to because when you're dealing with a table in a linear function, you're kind of thinking about your slope. You're changing by the same number every single time. Typically, this number is either added or subtracted. So let's create a table. Your tables can be vertical or they can be horizontal. So let's say that our x's go 2, 4, 6, 8. And then maybe our y's change and go -3, -4, -5, -6. So if you're testing to see whether or not this table represents a linear function, you're first looking at your y's and you're looking for similarities in the patterns. So this goes 2, 4, 6, 8. So each time it's going up 2 or adding 2 every time. This one, it's -1, it's getting smaller because -6 is smaller than -3. It's going down 1 every time. So since the x's and the y's are both changing at the same rate, this table represents a linear function. They can be added or they can be subtracted. Now you need to be careful because sometimes when I give you a table, I might leave out a number. And so you might be tricked into thinking that it doesn't change at the same rate when in fact it does. So always make sure that you're not really missing any numbers. Go ahead, close up linear. Let's look at exponential. So, in review, exponential growth gets very big very quickly. Exponential decay gets very small very quickly. When you're looking at an equation, you always want to look for the place for an equation that has an x in a power spot. If this number is bigger than 1, then it's growth. If it's smaller than 1, then it's decay. Again, whenever we're dealing with this, we're not looking at negative signs, so be careful there. Now, when we're examining a table and we're trying to decide if a table represents a growth or a decay function, the first thing to notice is, first, if it gets very big or very small. Since an exponential function is a relation by multiplication, you can a lot of times see that it's being multiplied by the same number or divided by the same number, but not always. Sometimes it's kind of hard to tell. So let's look. If my x is -1, 0, 0, not -0, 1, 2, 3. And then my y's, let's say we start at 1/2, and then we get 1, 2, 4, 8. We could even continue the pattern. Say the next one is 16. So, 16 doesn't seem like a very big number, but given the fact that we start at 1/2 and go all the way to 16, that would tell us exponential. Now, you might want to stop and think, oh, maybe this is linear. But in fact, if you start at 1 and go to 2, you're going up 1. Then you go from 2 to 4, you're going up 2. You're going from 4 to 8, you're going up 4. And then from 8 to 16, you're going up 8. So you're not going up at a consistent rate. So you can notice, like if you take 1 and you multiply it by 2, you get 2. If you take 2 and multiply it by 2, you get 4. You take 4 and multiply it by 2, you get 8. And if you take 8 and multiply it by 2, you get 16. So this is not an adding relationship, it's a multiplying relationship. This would be exponential growth because your numbers are getting very, very big if we were to try to continue the pattern. Let's try to look at an exponential decay. -1, 0, 1, 2, 3, 4. So let's say we start here at, we'll say 4, and then we get to 1, and then it's 1/4, then 1/16, then 1/32, then 1/64. So as you can see, we're getting a lot smaller very quickly. Continuing the pattern, you would end up getting very, very small, very, very fast, almost to the point where your calculator isn't even going to recognize that as a number. So you can tell that your exponential decay because you're getting very small, and you're kind of dividing by 4 every time. Although that is kind of hard to tell. And actually, I think I messed up. That should be 64. And that should be 128. So yeah, we're getting very, very small very, very quickly. So whenever you see it getting very big or very small, you want to look for exponential growth or decay. A lot of times when I ask you to predict a number, you should be able to kind of tell in the pattern whether you're multiplying or dividing by a number. Go ahead, close up exponential. Now let's do quadratic. Quadratic is probably the hardest thing to detect. When you're looking at a quadratic table, the first thing that I always try to look for is symmetry. We've talked about symmetrical parabolas many times and how they have the axis of symmetry, they fold on top of themselves. But looking at it in a table, sometimes it's kind of hard to tell. And it can even be a little bit distracting if you have a whole lot of numbers in your table. So this represents a quadratic graph. And a quadratic graph grows or falls, depending on which direction you're looking at. But it has repeats. So if you notice, we have 9 and 9. Well, that repeats itself. None of the other graphs repeats itself. Then we have 4 and 4. Then we have 1 and 1. And then we have this. This would represent our vertex. So if you see that repeating pattern, that would be the first clue that I would always look for. If you see repeats, it's almost always going to be a quadratic graph. But let's look at a different one. Perhaps I give you the part of the table that doesn't actually have a repeat in it. Maybe I only give you this half or something like that. So let's look at one, 2, 3, 4. We'll go a small table. And then we'll say that it's 2, then 8, then 18, then 32. It might be your first instinct to think that this might be exponential because it is getting big fairly quickly. But let's look. When we go from here to here, we're going up 6. Then we're going from here to here, and we're going up 10. Then we're going from here to here. Let's think about that for a minute. It's not a multiplying relationship, which is what makes it kind of challenging, because 32 minus 18, that's 14. So this isn't going to be multiplying, because if I multiply by 4, I get 8. But there's nothing I can multiply by 8 to get to 18. So this really isn't an exponential. If you notice, if you go from 6 to 10, those are 4 apart. And if you go from 10 to 14, those are also 4 apart. So another way to tell if you're exponential is to look at your second difference. If you're really struggling between exponential versus quadratic. All right, go ahead and close that up. Now, One more thing to kind of review before I let you loose to work on your assignment. You have, and you can put this at the bottom of your paper somewhere, but whenever you're dealing with x-intercepts and y-intercepts, and you're looking at a table, let me just make up a random function here. We've got x and we've got y. And let's say that we have, this might not be any type of special function, 0, 6, 1, 2, 3, 0, 4, -5, whatever. Okay, I just made this up. I really don't think it's anything special. It would just be a random relationship. If I'm talking about an x-intercept, if I'm looking at a table and not the graph, when you're looking at a table, you want to look where y equals 0. So your x-intercept is the point 3, 0 in this case. A y-intercept occurs where x equals 0. So in this case, your x-intercept is the point 0, 6. There will be some problems on your assignment that ask you to tell x and y intercepts based on a table. So I wanted to make sure you remembered that. Okay, now it's your turn. You have the rest of the class period to work on your assignment. It's the second page in your homework packet.